three use cases corresponding to the defense area. You will find that the three use cases are sort of related. They correspond to three different stages or styles of big data use within defense. They're all corresponding to a basic idea that defense is supported by, among other things, lots of sensors, whether sensors from either on aircraft or on the ground or on military or other vehicles. And that information, it covers all sorts of things from the weather, through video, through observation of other parts of the wavelength. And those are all transmitted somewhere to make decisions. And it's supporting that decision making that these use cases are implemented for. So here we have the rather general scenario. Defense is obviously associated with the real world. So we have three-dimensional worlds, and actually four if you put time into it. And visualization is very important because quick decisions are needed. And most of the information one gets is geospatially tagged. When you have a webcam, you know where that webcam is. And the amount of tagged geospatial data is rapidly increasing as more and more devices are automatically geolocated without any special action needed. So there is something called a geographical information system we'll discuss in the next slide. And that's actually familiar from Google Maps or Microsoft Virtual Earth. And it's actually capable of processing a lot of information. And the basic model is the one you see for the weather. In the weather, you get a basic map or maybe a basic satellite picture. And superimposed on that map, you have layers. Recently, we just had a big cold freeze, and the layers are sort of too cold to the coldness alert. Traditional layers, other layers are clouds, radar, and so on. So the GIS is built around taking the world, which is typically 2D, or in the case of Google Earth, can be 3D, and superimposing on that world information, either directly in terms of the color as in the radar, or as maybe a link that you can press to get further information. And typically, if you look at information that GIS display, they have two types, sort of bitmaps, which is blobs of data, images in various formats. And the other one is so-called vector format. You see that just in any processing on PowerPoint or anything. You either have a format that's trivially scalable, which is a vector format, because you have a logical description of the shape, or you have a bitmap. And objects, and then you have all these, this vector format has all sorts of different objects in it. KML is a very famous format popularized by Google for map data, and there are other types of related formats which are probably more complicated, and you obviously have to put them all in the right place. And there's obviously, when you're telling the command that the information corresponds to this point, it matters that it's this point and not a nearby point. Then when you take all this data, you need to do some analytics, like, can my tank go from A to B through C without getting stuck in the mud? And so that's the sort of path analysis application, which various software is around to do. And there's also they also want to superimpose weather simulation. That's where HPC might come in. And then to support, and then we might have a clustering analysis on some of the data. That's where principal component analysis and ICA come in. And what is the software for this? Well, historically, it's probably been geospatial relational databases with geospatial extensions. It needs those extensions because traditional SQL would not naturally support queries, which were spatial queries. Find out all the enemy soldiers in 2 kilometer by 3 kilometer window. That is not something SQL naturally supports. But there are clear extended databases and extended GIS systems that allow all of that to happen. Whether that's the right way to do it today is not at all obvious, given the probably clouds with Google Maps and the equivalent Microsoft product and Yahoo products have emphasized the value of having all this data stored in the cloud, and then your front-end client gathers the data from the cloud, all the basic map data and all the overlays, and presents it to you. And the point, and this is then the point of this futures. This intelligent. This is called an intelligence system because this front end, this GIS front end, is gathering data to make intelligent decisions, which are obviously critical for the military. And visualization is critical. We have the warfighter, first responders in the front. They might only have cell phones, and so you need to be able to have these things automatically run at the resolution appropriate for display on small devices. Further, for the military applications, everything is security is critical, and you need to make certain that when your soldier's captured, there's information on his handheld is not compromised. So this is a pretty challenging application, but this is an application that's been studied for an awful long time. And this is sort of called command and control and systems that we've built for a long time. What's interesting over the last 15 years, the commodity application has come along, and that used to be called disaster response and crisis containment. That when you have an actual crisis and you like an earthquake or a fire or freezing weather, you have the same types of issues in decision making that you do in the military. So these command and control systems used to be specialized to the military, but now earthquakes, like the nuclear meltdown in Japan, those all actually need the same technology. So this is actually now broader based. So here we have a GIS described. Esri is a dominant company in this field, producing commercial products. And of course, we have the standard web products. And on the middle right, we actually have a typical GIS display with a map and various overlays. We have here a drone gathering data. Here we have sensors in a helmet gathering data in case the soldier's injured. And here we have some data gathering truck. We look at the classification. We have parallelism over sensors, parallelism over people accessing the data. It's clearly streaming. We need to classify the data according to its implication. There's lots of pleasingly parallel computation. Every image can be analyzed independently to find out what it's saying, and we need the GIS to display it. So those are the categories. Here we have the second slide in this, which is use case 14. And this is focusing on the image aspects. I said right at the beginning that imagery was a huge driver of big data. And that's particularly true in the defense area because they have so many sensors gathering so much data. And it says here they can get petabytes of data in a few hours. So that's because you have data which has high frame rate and is very high resolution. 1080p standard resolution familiar from high definition TVs through these 10K by 10K pixel full color resolution images. And all of this stuff has to be put as one of these overlays, which I mentioned on geospatial displays. The images must have analytics applied to them, which are typically going to be probably machine learning analytics. And that's going to be able to identify objects. The NSA and related agencies have been taking images and tracking the individual people and vehicles and buildings from those images for an awful long time. When I used to work in this field more intensively around the late 80s, we were doing exactly this problem. I used to work on how to do optimal pathfinding in complex terrains with multiple vehicles not interacting with each other. So that's a standard type of problem that we used to do. So being imagery that's suitable for GPUs, and so somehow doing this GPU processing, also doing it in the right place. Remember, you have your sensor taking these high definition images. Is it really possible to put a GPU cluster near that sensor if that sensor is either in an aircraft or in a rather sensitive area where there's a lot of hostile action? So there's some very non-trivial issues here. And that comes back to this bottom. It says transmission of data from sensor to system is a challenge. The logical thing is to have the system in the cloud and then the sensor data out in the world and transmit from the sensor to the cloud. But it may not be possible. There may be too much data. So this is a very serious challenge in this field. How much processing to do locally and how much processing to do at the back end. Finally, we have for this defense area, the last use case is sort of the final step, which is supporting the intelligent decisions. This is actually called Fusion. We'll describe Fusion as an application on use case 16. And so you need to take this this is a classic problem. You have diverse data from lots of different sources. You have harried analysts and commanders and decision makers sitting either at their home, in front of CNN, or more traditionally in a command center with hundreds of displays around them. And they need to be able to make correct decisions. So a huge amount of processing is needed to just give the analysts the smallest amount of data possible to make decisions. It's easy to give them everything, but there's too much data. And as we get the bigger and bigger data, we're going to make better and better decisions as to what to present to the decision maker. So more analytics and intelligence is needed to make these decisions. So it says here, identify relationship between different entities, spot trends in sentiment or intent, find location and timing of hostile actions, including explosive devices, track the location and actions of the hostile actors, people, vehicles, and so on. Reason, think about what it implies and derive knowledge from diverse, disconnected, unstructured, e.g. text sources mentioning an attack or mentioning a terrorist name. Process the data as close as possible to the point of collection to minimize data transmission, but at a point which is safe enough that you can afford to have enough computing. So these are serious challenges. And then we have the software, which involves standard NoSQL, big table software, Hadoop, processing natural language for the text data processing. We need Puppet, which does deployment and security. Storm is a Apache big data streaming software. And the data varies in size from tens of terabytes to hundreds of petabytes. With the image, which as we pointed out, the imagery intelligent devices is gathering huge amounts of data. The actual warfighter on their own, was first responder for the civilian crisis management application, would only have up to 100 gigabytes sitting in their handheld data storage. This data comes from wide different sources, both the civilian version and the military version, and you need to integrate this all together. That's this fusion problem. And it's actually a typical of the challenge of today's world, which actually today has made a lot of progress in fusing and integrating results from different sources and using some automatic analytics to make good decisions about how to do that fusing by using effectively the analytics to discover previous known correlations between data from different sources to find that same correlation in today's data and then what its implication is. So these three use cases have covered in three different steps, the aspects. The the broad visualization of GIS and presenting of data in use case 13, the processing of the image use case and video in use case 14, and in use case 15, the fusion of the data to allow the analyst to make real decisions. So that's the end of this military area, and now we move on to healthcare and life science.